All right, welcome to module number 2 of the BEST program. This module is referred to as Basic Design and Engineering. And in this module, we're going to have certain learning objectives and things that we're going to discuss. Of course, a list of those objects or those objectives are going to be looking at basic industry standards. We're going to look at the entire industry and look at the most commonly used standard details. We're going to talk about what recognizes or how to recognize a SIP-friendly design. So when we look at a set of architectural blueprints, we know whether or not we've got a design that is friendly towards SIPs and whether or not we can effectively put SIPs into that package and create what the architect has drawn. We're also going to talk about what a designer goes through in determining how to incorporate SIPs into that design. There's a lot of decisions that a SIP designer has to make in order to move forward into creating that SIP envelope. We're going to review common connection details, starting from the ground and working our way right up through the top of a structure. These will be standard details like wall-to-wall, wall-to-floor connections, and moving our way through. And we'll talk about those various details and things that are important to recognize as we talk about them. And during this entire module, we're going to talk about the engineering concepts. We're going to be talking about basic engineering concepts. We could go on for hours, if not days, to talk about engineering and how it relates to SIPs, but we're going to keep it down, simple, on terms that a builder needs to understand as it relates to working with SIPs. Now, as we go through this module, it's important for you to understand that we're talking about standard details that are used throughout the industry. We're going to be showing details that are used by the majority of the manufacturers with the industry. It's not all the details. In some cases, this panel provider that you're using may be using details that are outside of what's going to be discussed here. That's not necessarily a bad thing. It's just for the limited time that we have in this module, we're going to talk about the most commonly used details. So it's important that you understand that. When working with structural insulated panels and the manufacturers that provide them, all manufacturers that are working within the SIPA industry or the association, they all have third-party testing, they all have code approvals, and they also have load design charts. And it's these load design charts that you see that give the basic information that both architects, designers, and engineers utilize in making the design decisions to determine how the panels are going to be joined, the thicknesses of panels that are going to be used, how far the panels can span. And it's beneficial for you to understand that these load design charts are not only available, but how to use them and know when you're asking a panel to do something beyond its capabilities. Now, let's start with the simplest, most common details that we're going to see in the SIP industry. And first and foremost, the number one detail is going to be the spline detail. This is where we have either a wall or a roof panel-to-panel connection in plane. As you see here, we have what's also known as the surface spline connection. Now, this surface spline connection means that we're doing some really good things. We're letting the panels do all the work. So from a design perspective, this detail means that we're not incorporating additional wood. We're not, from an engineering perspective, asking the panel to do more than it can do and therefore having to add wood or additional support to the system. We're letting the panel do all the work. So this detail is very nice, and also from your perspective as a builder, it means you can put up the system faster. You don't have wood for thermal bridging, so it becomes more energy efficient. It's a speed issue. It's a cost issue. It's a great detail to incorporate into your design. The surface spline, as you see here on the left side, can be a mini block spline, also known as a super spline. Some people have even referred to it as a mini SIP. Basically what we're doing is we're taking a smaller version of the structural insulated panel and we're incorporating it into the edges of both panels and stitching it together with the appropriate fastener as specified. Now, if we're not using the block spline, we can go to a separate surface spline. As you see on the right, we have a condition where the panels are edge grooved or routed to receive single layers of ripped either OSB or plywood, depending upon the manufacturer that you're using. And in this detail, we can then combine one panel to the other with nailing on both sides of the joint, and now we've got a firm joint from one panel to the next. The sealing issues that go into either of these cases are going to be a function of using the panel mastics that we'll talk about much more throughout this rest of this whole program, as well as potentially single component or two component foams. So the sealing issues, and we'll talk more about that through the installation process, but from a design issue, this is the joint that you're probably going to see most commonly used. Next, we can go to the same panel, but instead of using a surface spline condition, we're going to use lumber. We're going to insert that lumber so that it is half into one panel and half into the other. As you see on the left, we're dealing with a situation where the lumber is a single component piece. That could be sawn lumber, it could be engineered lumber, it could be an LVL, or even a glue lam if necessary. And that piece of lumber combines the two panels together, where it's then again stitched and nailed on both sides of the joint, both sides of the panel. Now, if we can't do what we want to do from the engineering standpoint with a single piece of dimensional lumber in the spline joint, then if we look at to the right side, we can also consider using a double dimensional lumber spline. If we use this double lumber spline, we get additional support to resist the transverse load which is applied to that panel. So now that if we're up on the roof and we need to increase the capacity of the panel because of an increased dead load or a live load, we can carry that load based on the fact that we have two pieces instead of one of lumber, and we've beefed up the joint so that we can carry more load. One of the other common details that you'll see is the I-joist spline connection. Now this I-joist spline connection, very similar to the one that we just looked at previously. It's just using an engineered lumber component or an I-joist, very similar to what you're framing up typical floors with. And in this case, the I-joist it's a little bit lighter. It has a cost differential, but it also adds more value in that it's easier to handle, it's lighter, it goes in perfectly smoothly because we don't have the problems with sawn lumber wanting to bow, twist, or check. We also have a wider top flange, so we get a nice easy way to attach from one panel to the next, and it slips right into the panel. Some manufacturers will make the panel recessed, completely squared off, so that you have to have a foam insert, as you see on the left-hand side, and some manufacturers will edge treat this panel so that the foam is cut in such that the I-joist slides right into the edge of the panel, and there is no foam attached to that I-joist, as you see on the photo on our right. Again, standard detail, commonly used. If we look into the cam lock system, which I'm sure a lot of you have heard about, that is a fastening technique that is specific to the urethane manufacturers. Now, it's a great system in that it gives us a lot of speed and it allows us to put panels together very, very quickly. But when we have the good, we also sometimes have the bad. And the bad is it has a limitation in terms of its design flexibility. Once our design gets complex and the panels get smaller and smaller, we have cam locks that are only spaced so close together, so therefore when our complexity of our design increases, the ability to use cam locks decreases. And then we have to go back to the details or the connection details that we've already talked about. It's not a bad thing, it just means there's a limitation when you get into these complex designs. Now let's talk for a moment, after we've talked about these most common details of connection, let's talk about when you look at a set of blueprints and you decide or make the determination whether or not you want to go into a SIP envelope, what makes a SIP friendly, or what is a SIP panel friendly design? You might look at the friendliness based on whether you're considering floor panels, wall panels, or roof panels. Let's start with the floor panels. As we've said before in the previous module, floor panels aren't commonly used, and not be for a variety of reasons. But if we are going to use them, the areas where they might work really well is if we're doing small additions, if we're building on top of pilings where we have Mother Nature blowing underneath of the structure and we want the insulating attributes of a SIP used towards our benefit, that's where it starts making good sense. So if we're building at the beach on top of pilings, or at a snow resort up on top of raised up off the ground, that's where the floor systems start to make sense, and it's a panel-friendly issue. If we talk about wall SIPs, where can wall SIPs be used? It doesn't matter what you can roll out and look at. If it's been designed by an architect and designed for sticks, SIPs will work just fine. There's no limitations when you are looking at a wall use of SIPs in any application or any design. The roof SIPs, of course, are a different issue. A lot of misperception follows whether or not roof panels should or should not be used. In some cases, the answer is no. Let's not force SIPs into the design. Trusses work incredibly well. That's the way the building was designed. That's the way the foundation was designed, is to be built with trusses. We've got flat ceilings, and it works perfectly well. If we're only going to use wall SIPs in that scenario or that design, so be it. But we also have some, what we like to refer to as a panel-friendly architectural styles, which very conveniently incorporate SIPs into their design. And you see this list that we've listed. It includes things like bungalows, the craftsman-style houses. We move to Cape Cods and A-frames. You get into these designs where insulation moved up into the roof as opposed to a flat ceiling works very, very well. And of course, that's what SIPs do incredibly well in a roof application. They take the insulation, they move it to the roof line, and they give us additional living space. So when you start working with these types of styles, moving down the list, we're talking about modern designs. We open up and give us big vaulted spaces, dramatic looks inside. That's where the SIPs work. Of course, timber frames and hybrids. Hybrids is what we refer to as the combination of using wall SIPs for our structure and incorporating certain timber frame elements inside of that design. And I'll show you some, or we'll look at some details here a little bit later on when we talk about hybrids. But of course, the timber framing, as we talked about in the first module, is really one of those things that kick-started SIPs and started making it work very well. Now, as the builder, you need to ask yourself when you have a set of blueprints or a customer that wants to move into a SIP project, you need to ask yourself, all right, do I need an architect or a designer? Which one am I working with and which one makes sense? You have to understand that these are two distinct, different occupations. The architects, they typically will design a custom design based on input that is provided to them, and then they don't necessarily need to or have to design that structure specifically for SIPs. That's where the designer may step in. The designer might be viewed as one tier down from the architect because he doesn't have the education or the knowledge that architects typically have. But what they may have is knowledge about SIPs that the architect does not have. It is the SIP providers, the manufacturers, and the people that do SIP-specific drawings that we're going to be talking about a lot that have the knowledge of what SIPs do, how they go together, what engineering capacities they have to meet certain criteria such that they can utilize SIPs to their most effective or the most highest optimization. The designers have the ability to do permit drawings. They have the ability to take the architect's drawings and convert them over to a SIP drawing. And we're going to talk about that later on in the program. There are certain design considerations that you need to talk about or think about when you start working with a complete SIP package. And first and foremost is, our construction drawings, do they need to be designed for SIPs? And that's where the architect may have designed a building, but not necessarily designed it for SIPs. That doesn't mean that it can't be converted to SIPs, and that's where the designer steps in. You also need to ask yourself right off the bat when you look at a set of drawings, is does the structural engineer need to review these SIP shop drawings? And that's something that has to do with the municipality and the code officials that you're working with. And of course, as always, the first thing you should ask yourself when you roll out a set of drawings is, are roof SIPs really the best option for this package? And in a lot of cases, the answer is no. And it's not necessarily always in your best interest as the builder to try to force a product into a design that really just doesn't work for it. Now, when we talk about design, the designers of the SIP industry will typically, most often, work with CAD, computer-aided design. What does that mean? Well, first of all, this CAD design is how the designers incorporate what it is that the architect has drawn into a SIP panel layout drawing. And we use that term quite a bit. It's a panel layout drawing. It's not to be confused with the architectural drawing. Think, if you will, a little bit about the difference between trusses and the architectural drawing. There's a lot of similarities in there. The architectural drawing draws a roof system and specifies the trusses, but the architect doesn't go through the evolution of designing the entire truss package. That's up to the truss provider. So think of the SIP provider very similar or closely aligned to what you might consider the truss provider. Okay, they do a specific design that relates to the SIP envelope, and that complements the architectural drawing. So there's not a problem with these designers taking stick frame drawings and converting them into a SIP panel layout drawing. They typically work with AutoCAD or any type of CAD design drawing. There are some specific CAD design packages that have been designed for the SIP industry. Most notably are the HSB CAD and the Dietrichs, and CADWorks to some extent. And all of these programs allow the designers to create the envelope in a SIP package And then what we do is it converts seamlessly into a CNC program. And this is the term CAD-CAM, where we have computer-aided design, which translates into computer-aided machining or computer-aided machinery. And this makes for a seamless transfer for many of the manufacturers who have the capacity or have CNC equipment. They design in CAD, it moves right into CNC cutting, and you get a quick turnover. The 3D CAD, when they design, also does a very good job at catching complex issues as it relates to fitting the panels together. If you think about the thickness of a panel and complex roof joinery, when we design a building in a 3D virtual environment, what we can do is we can, in that 3D world, figure out how these panels are going to combine together properly when cut in a CNC environment. The thickness of the panel means that with compound angle joinery or compound cutting, you have to be dead on the saw angle in order to be able to incorporate complex hips and valleys so that they come together and the joint works perfectly. Okay? So it's these CAD designs working in a 3D environment that solve a lot of these engineering issues that we want to work with. Now what you're seeing here is the evolution of the design, moving over to the manufacturing of the panel and knowing exactly how much we need to fabricate or laminate. And then we drop down into fabrication, where it's actually the CNC fabrication, and moving over to our bottom, we see now the finished fabricated panel. And now we're ready to ship to the field and assemble it exactly as the CAD designer designed it. So let's talk a little more about the SIP designers. A good SIP designer has a very important job, and what they need to do is they need to control, in much like a juggler controls 3 balls, they have to control the needs of the engineer, of the budget, and of the installer. And all of those things combined together have to work to produce what it is that the architect or the designer of the project has drawn to create the finished project. The designer needs to control all 3 of these elements, because obviously the engineering of the project needs to be satisfied. The designer, a good designer, thinks about the installer and how they can efficiently and effectively work to put panels up so that they don't run into problems in the field. And of course, you've got a budget. It's very easy to throw all kinds of additional lumber and cut the panels all up so that you get the best possible yield and the manufacturer doesn't have to maybe produce as much area, but it doesn't necessarily help either the engineer or the installer. So it's truly a juggling act this SIP designer needs to work with. As they put all of this knowledge of SIP engineering and design possibilities together into their design drawings, they need to create a set of drawings that relays all of the critical information, that is the details, the sections, and everything up combined with the engineering requirements, so that we have a SIP panel layout drawing that then allows us to move forward. And we're going to talk about SIP panel layout drawings later in this program. It's important for you, the builder, as well as the designer already knows, that buildings are built from the ground up, but they're designed from the top down. When we start with a design, we always look at the roof first, and we figure out how loads are coming down through this building. It's engineering 101. It's what the designer starts with. We look at the roof, and we follow those load paths all the way down through, so that in a 3D environment, as we design this, we know what's happening down at the bottom level, so that when we get to the top, we've satisfied all those engineering requirements. Now, there's a lot of decisions that this designer will make while he goes through the process of designing this building. And first and foremost, he's got to ask himself, well, are SIPs really going to be used? Now, this is probably a question that you, the builder, have already asked yourself and made the determination whether or not it's SIP friendly or not. But now you don't need to know where you're going to incorporate SIPs and where you're not, where you're going to leave it to conventional framing or some other style of building that incorporates or works in conjunction with the SIP package that's being provided. Then one of the number one questions that's often asked is, what is the thickness of the panel that we're going to use, or what size panel? And this has a lot to do with the conditions of the job site. Maybe it has to do with the capabilities of the panel provider. But you need to understand, as the SIP designer looks at this package, needs to know what thickness panel are we using and what size panel. The thickness is most often a function of people's perception that our value and the requirements of our value rules the thicknesses required. In some cases, that's really not the case. The total energy modeling of a package can in some cases allow the SIP designer to use a thinner panel that might have a lower R value, knowing full well that energy modeling of the entire structure still meets the intent of the code and allows you to design with a slightly thinner panel.
Now the question we have to ask ourselves as the designer is, what thickness panel do we want to use in order to meet the engineering requirements based on the panel span? A panel has the ability to resist transverse loads before it wants to bend or bow. So as the designer, when choosing the thickness of the panel, we look at all the engineering forces applied to that panel. How far is the panel spanning from point A to B? This can be in both the wall or the roof. If we have a tall wall, we may need a thicker panel, not because the code says we need the R value, but because we want to resist the forces such as wind, which is a transverse load applied to that panel, making it want to bow.
So these are the things that the panel designer has to ask themselves. One of the most important things that they look at when they look at a architectural design is, hey, how are we holding this roof up? If we have SIPs in a panel package, how do we hold the roofs up? Remember, if we talked about trusses, trusses do a great job at spreading all of this load to the front and the back wall or the side walls, depending upon the orientation of the truss. What the SIP panel package does is it incorporates more point loading because the panel has to span from either the eave to the ridge or gable to gable wall, and now we have a combination of either uniform or point loads coming down through the middle of our structure. You have to account for that through the incorporation of beams and purlins or trusses and rafters and perhaps interior load-bearing partitions. All of those things have to be thought about by the panel designer when they look at this architectural drawing and say, how are we going to incorporate SIPs into this design so that it works? They look at the height of walls, they look at the spacing of all of their fasteners based on the engineering environment, which could include high winds, could include seismic issues, all kinds of engineering things that are forces that are applied to this structure, and they have to use the knowledge that's given to them by the data that is used or provided by the SIP panel manufacturer so that they get a design that works and takes care of those three balls that we talked about. Remember, you've got budget, you've got engineering, and don't forget the installer, because you as the builder, you're often the installer. And if the designer doesn't take your needs into consideration, then when you're out there putting this panel package up, you may realize that you're doing a lot more work than you have to or that you should have to. All right, all of these things are thought about by the panel designer. All right, at this point, we're basically going to talk about, and as you can see behind me, we're going to talk about building this house with standard connection details, starting from the ground and working our way up. It's a cursory overview of the details in the most basic sense. First and foremost, if we have floor SIPs in this particular project, let's look at this detail and see how SIPs might be incorporated into this panel package. As we've said before, floor SIPs are not commonly used, but in this case, it shows a good detail of how a floor SIP might be incorporated as it comes in and bears on the foundation, and then a wall SIP or even a conventionally wall frame package might bear on top of it. What considerations are being looked at when we start talking about floor SIPs? Again, span determines the thickness. The greater the span of the floor system, we have to go with a thicker panel. Then we also need to look at, do we need some type of a substructure or a girder system to shorten that span so that the panel will work just fine? We need to know how we're going to connect those floor systems to the foundation system. And here's a real important key, is that we have the need or the requirement to incorporate, in a lot of cases, a second layer of sheathing or substrate on top of the SIP, so that the point load resistance or capacity of the oriented strand board skin is not exceeded, because if we have a point load such as a high heel or something of that nature, or a stool leg, it can deform or depress into the OSB and overcome the point load resistance of oriented strand board. So it's a key that if you're dealing with a vinyl floor or a carpeted floor, in a lot of cases, you now need to put another layer of sheathing over top of that floor system. If we're putting SIPs in the floor, we've got to have concerns with things like utility runs, and first and foremost, the most important thing about dealing with floor SIPs is protection from the weather. If you have a floor going down first, it's going to be potentially exposed to the weather the most and the longest. This has nothing to do with design and engineering. This has to do with you, the builder, thinking about whether or not floor SIPs are really the best choice for this particular project. That's why at the very beginning we talked about small additions and working up on top of areas of top of pilings where floor SIPs really make sense. This is where we want to go through the extra effort to protect them from the weather so that we can utilize them and not worry about weather or moisture related concerns for a horizontal floor that can potentially hold water. And then if we put another layer of sheathing on top of that panel, we're now talking about trapping moisture. So it's really important before you consider using these floor SIPs. So the designer, when working with floor SIPs, they need to determine all of those various things. The next thing as we move up is the wall SIP. If we're working with a design that is incorporating the SIP into the wall orientation, there's a couple things that determine the thickness that are going to be used, and this is what the designer has to take into consideration, or what you have to take into consideration, and that is what determines thickness may be the R value. It might be the height of the wall, because as the wall gets higher and we have those wind forces or those lateral loads applied, we potentially need to have a thicker wall or incorporate additional lumber into that wall to resist that bowing or that lateral force. The other thing might be energy modeling. As I said before, R value should not necessarily reign supreme in your decision or your determination is to consider how thick a panel should be. Energy modeling used to determine the energy efficiency of this structure can be utilized in essence to determine what R value truly is needed. So all these things need to be taken into consideration. If we're talking about wall SIPs, we have a couple of standard details that we're showing you here that incorporate the wall SIP as it attaches to the floor. Now, I say floor, it might be directly to the foundation. What we have here is a wall panel that goes down and caps the end of the floor system, and the foundation actually shares the support of both the wall as well as the floor system. In essence, what we've done is we're moving away from platform framing where we build the entire floor system and then we put the wall on top of it. Why do we might want to consider doing it this way? Because the leakiest part of all buildings being built today in the conventional term are usually the floor systems. If we find and look for air infiltration or exfiltration, the next time you do a blower door test and you've got a platform framed floor system, you're probably going to find that the vast majority of your air leakage is coming through that floor system. So the detail on your left very clearly shows that the floor system is now encapsulated inside of the envelope. We don't have that disconnect, if you will. We don't have to go back in and insulate floor cubbies. It's a nice way to do it. But of course, you've got the consideration of the foundation being wide enough to bear both the floor system as well as the floor system as well as the wall system. In the middle, you can see that typical platform frame system where you have a floor built first and the wall panel goes on top of it. Again, here you need to look at, we have to go back in and insulate that floor system. If we're building slab on grade, which of course a lot of builders do depending upon which area of the country they're building, here's a simple detail that shows the wall panel coming down, attaching directly to the floor slab. The one key element here is a capillary break, because you're dealing with, in most cases, again, a wood-framed SIP panel. That wood needs to be kept isolated from the concrete, because concrete wicks water, and if it can wick water up to the top and the wood is in direct contact with it, it'll wick water on up into the edge of the panel. So we need that capillary break to make sure that we don't allow water to continue on through. Some manufacturers will use what's known as an insulated rim panel. It's not necessarily a very widely used, but it's certainly a good option, because what it allows you to do is put that insulated rim and give you the insulating air tightness in your floor system that I just mentioned is often a source of a great deal of air leakage in and out of a structure. And in this photo or this detail, you can see that the insulated rim acts as the rim board, and now we've got a platform framed floor system that's very tight and well insulated with the wall panels going on top of it. As we move up through this structure, the wall panels have corner connections. As you can see on the left, we're looking in plan view at a typical right angle corner connection where we've got dimensional lumber in the end of both the short wall as well as the long wall. And you've got a lap there. That lap means that you've got one wall runs short, one wall runs long, and let's make sure that we've got those thought about and the dimensioned properly when we go through the design drawings. It's very important when you wind up with two longs or two shorts when you get to the corner. That doesn't work always so well. The detail on the right shows that if you're working with a bay or something other than a square 90-degree corner, doesn't mean you can't have the panel fabricated so that it fits together and gives you the angle that's necessary to get you through the design required. Key to talk about here just for 1 second is the intersection into the wall panels of all our interior partitions. It's not standard to use a SIP in an interior partition for a whole host of reasons, most of which has to do with cost and the ability to run mechanicals through those interior wall partitions. But we do have interior partitions, and where they intersect with that SIP panel, it means that we need to make a firm connection. Knowing that the panel has a skin that might only be 7/16 OSB, it's not necessarily a good idea to let your framing crew just spike an interior stud into 7/16 OSB and think that that's going to be good enough. This is why the detail that you see here on the right shows a panel screw, just like we've used panel screws everywhere else to tie the panels together. We're going to run that panel screw all the way through the panel into that interior partition and get a good firm connection. If you don't, any movement that occurs in a building naturally over time may result in some separation there and, of course, a drywall crack. And the last thing you want to deal with as the builder is a callback to come fix a drywall crack. It's not something that you're going to be happy with. As we move up the house even further towards the roof, we get to the intersection of a mid-level floor system. In this case, let's say we've got a 2-story house. We get to the top of our first floor walls, and we're going to put a floor system on. Well, in most cases, platform framing, as you see on the left, is the typical detail which most conventional framers use. The top of the wall, they platform frame the floor system, and then they start anew on top of that. However, you can do the same thing with SIPs in a platform configuration, and again, it's that floor system that may lead you to a lot of air leaks that you're not going to be happy with, or an obvious choice may be what you see on the right, which is what we refer to as the hanging floor system. Now, a hanging floor system uses a commonly available top mount hanger that will allow the floor joist to be hung off the top of the first floor wall. In this detail, you can very clearly see that it is the first floor wall panel that comes all the way up and caps that floor system to prevent any air movement out through the exterior via your floor system. It's a great detail, and here's a photo that shows very clearly how it is not only clean, but it's also very, very energy efficient and allows you to move forward. The thing that you need to be aware of is when you do a hanging floor system, in some cases you have concerns about moving your electrical from one system to the other because you don't have the advantage of dealing with that floor system to work inside of. But one of the big advantages that the hanging floor system also gives you, it increases the diaphragm capacity of that connection between the floor sheathing and the wall itself. It's a great system. It goes up just as quickly as a platform frame system, and from an energy standpoint, it can't be beat. Let's continue working our way up this wall panel. We're now on a second floor. We've got a wall panel package that is going to support a roof panel. We have a couple of options when we get to the top of this wall. We can take that panel and we can have it bevel cut, and in some cases, the manufacturer has the ability using CNC equipment to provide the exact bevel necessary to receive that roof regardless of what the pitch might be. And at the top of that wall panel, as you see in our detail here on the left, the top plate is recessed into the top of the wall panel, and then ultimately it will receive the fastener or the screw that comes through the roof panel into it. It's a detail where you have to concern yourself with the potential air movement between the top of wall and the bottom of the roof, and that's a critical sealing area. The picture on the right shows you how the panel has been put in place, the foam has been recessed, now ready to receive that top plate, and in that same photo you can see the gable wall panel where that top plate has already been installed. The other option besides bevel cutting the top of your wall panel is to square cut the top of the wall. In this case, the panel is just that. It's square cut, and now we have a couple of options. We can build up the top of that wall with beveled lumber or lumber that has been ripped to the roof plane so that it now will receive and support the bearing load of that roof panel. In some cases, the top of that wall is going to receive a truss. The truss doesn't want a beveled condition to set on top of it, wants a nice square top of wall. Therefore, the panel's cut square and the truss sits right on top of it. We can mix and match those truss systems with a wall panel system without any problem. Now, the truss package is in essence a small point load, depending upon the size of the truss. If that point load exceeds the axial carrying capability of the wall panel, we may need to put what's referred to as a shim plate on top of the wall panel. You can see in the diagram on my right that that shim plate increases the load carrying capacity, the axial load carrying capacity of that wall panel, because it puts full bearing on both the inside and the outside skin. That's an important detail that the designer has to be able to work with to increase the capacity of the load of that wall panel without having to put posting inside of the panel to receive that point load. That's critical to understand. As long as we're building walls, we put windows and doors in walls, and above those windows and doors may or may not need to incorporate headers. What type of a header? A structural header. Whether that header be dimensional lumber or laminated veneer lumber, some type of engineered wood component, we need to know, as the designer knows, whether or not the panel system and its configuration require us to incorporate that header. Well, when do headers need to be used? Or do they not need to be used because the panel system has the structural capacity to carry those loads? There's a couple of things that we need to look at very closely to determine whether or not that header is needed. First and foremost, how wide is the opening? You could throw around some rules of thumb and say that in a standard scenario with a standard design, if windows were less than, say, 4 feet wide, you may not need to put a header, assuming that you had a certain amount of panel area above or a certain amount of height of panel above that opening. You may not need to incorporate a header. The panel can do the work. So in an overview, we need to look at the size of the opening, how much panel there is above the opening, and of course we need to look at the load above that. If we have a point load that's directly over an opening, a window or door, then we're going to need to incorporate some type of a structural header to carry that load on and around, down around that window or that door opening. There's ways to incorporate SIP headers, and the SIP manufacturers have the testing and again the load design charts to show or be able to calculate and to determine whether or not a SIP header can be incorporated and carry that load. It has a certain capacity, and once you exceed that capacity, the SIP header no longer works, and we need to start looking at some other options. In this case, what can those headers be? Well, if they can't be a SIP header, then we might have to look at a built-up 2x system, an engineered wood component. We may be able to use some of the many insulated components that are available, or insulated headers. And then what's carrying that header? Well, does it need to be a post, a jack post? Does it need to be incorporated into the wall panels on either side? These are things that the engineer looks at using the data that is provided by the SIP provider. They have the load design charts to know what their panel has been tested and what it can carry. But it's important to know that we don't necessarily need to throw headers in all of our doors and all of our windows just because a designer is taking the safe road and saying, well, I really don't understand how this system might work or carry these loads, so I'll just arbitrarily throw 11.25-inch LVLs over top of every single window. That doesn't necessarily make sense. It's not juggling the balls properly, as we talked about, when you're controlling things like budget, and also you as the installer, because you don't want to make up all of these LVL headers and install them when they don't need to be provided. Now, once we've answered the question about whether or not headers are needed above doors and windows, we also need to look at the entire system in terms of point loads. Remember what I said earlier. Houses or structures are built from the ground up, but they're designed from the top down. And the reason we design from the top down is because of point loads. If the SIP roof system, or whatever type of roof system it is, has certain beams or trusses or elements that create point loads within your walls, they have to be looked at very closely, because the panel, although it's very strong and has the capacity to move a lot of force down through both of those skins, it can easily be overcome with a large ridge beam or a purlin beam or a truss that has a lot of end reaction that puts a lot of weight or load right down through a specific area of that panel. So how do we handle these point loads? Well, in the not worst case scenario, but what is commonly done, is we put a post inside the panel. The designer determines what the loading is in that area of the wall panel and incorporates a post very clearly into that wall panel to carry that load down through the wall system into the foundation. As I said before, when panels are square cut, In some cases, we have the ability to put a shim plate on top of that wall, and we distribute that load so that we don't need to put that post in. By not putting that post in, we save the cost of the post, we save the time of incorporating that post, and again, you, the builder, have the ability to move quicker. In the best case scenario, the point load is determined through calculation to be such that the wall panel will carry that load down through both of the skins of the panels. And even though it's a point load, the SIP panel is carrying that load all the way down through. That's the best of all possible worlds. These photos that you see are two different ways to carry point loads down through a wall panel. And in these pictures, we're also showing how the point load carries down to and around window openings. The picture on your left, obviously we have a large ridge beam. That ridge beam comes into the top of the gable wall, and where those gable panels come together at that point, we are carrying through posting all the way down through those two windows down into the floor system or the foundation below. If we look at the picture on the right, we're dealing with a very similar situation in that we have a ridge beam and we're posting down through, but we're hitting that header. And once we hit that conventional header, that point load has been determined that one, a header is needed, and the posting, when transferring the load to the header, now carries that load around the window opening into jack posts and on down. So point loads are something that you have to be mindful of as to how you're going to get that load down through your wall system and around and into the foundation. While we're still talking about walls, and we've put a bunch of windows and doors, we've dealt with headers, we've dealt with point loads, the one thing that the designer needs to pay particular attention to is the lateral force that is the wind. These two photos show good and bad examples of designs that one handles the wind force. The one on our left, the one on my right doesn't do a very good job. Now both of these pictures are within timber frame structures, but again, the one on the right puts a big dramatic tall wall with a whole bunch of windows in it with no good way to resist the force, which is that wind. Now this panel is being asked to do an awful lot of work, and in essence, you may, as the designer starts to calculate those loads, require you to put a lot of lumber or maybe even steel inside of this wall panel to resist that force. The design on your left is one that works a whole lot better to handle these lateral forces. And it's these lateral forces that are the determining factor in what the thickness of the panel is and how we design the components inside the panel to resist those forces that are being applied to it. When we talk about tall walls, we're concerned about these walls that are going to move in the wind. And a rule of thumb might be construed as tall walls are defined anything that's greater than 12 feet high when you're working in about 110 mile up to 110 mile an hour zone. If you get into a 120 plus mile an hour zone, a wall that's only 10 feet high might be construed or thought of as a tall wall, and you have special considerations to deal with to prevent that bowing or that movement. In some cases, it's a engineered wood product, which creates a stiffener, and the worst case example is we now have to start incorporating steel into this wall panel package just to resist that force. So when we think about good design, we want to think about what's going into that panel package that you, the builder, have to, one, pay for and install. We don't want to put more than we have to, and good design allows us to do that. Okay, we finished talking about walls. And as we continue to construct our building from the ground up with all these various details, we're going to go into the details of the roof. But as we think about the designer, as well as you, the builder, again, you need to start asking yourself some certain questions. And the first one, again, is what determines our thickness? Well, what is the key element that determines our thickness, again, is what is our span and what is our total load. The perception is our value always determines the thickness. And again, you'll hear the clients routinely say, well, I have to have this minimum R value, so it has to be this thickness panel. Again, if we incorporate energy modeling and we go to that extent, we may be able to actually use a slightly thinner panel when modeling the entire structure and knowing that we still meet the intent of the code. But the determination of the thickness of the panel most oftenly should be determined based on what is our total load on that roof and how far is it going to span. So we need to look at the roof support structure and make that determination to determine how thick that panel is going to be. And then, of course, we need to go back to think at the beginning of this module, we talked about the different connection details and whether or not we were capable of using a surface spline connection, or did we have to start putting lumber inside of our roof panels to help meet that span requirement. Because as we put engineered lumber or rough sawn lumber or the I-joist into these roof panels, we increase the span capacity, but we also have to remember that we increase the cost. And you, the builder, who's the installer, may slow down a little bit because you have to deal with all of these extra elements that go into the panels. You may be able to span further, but you added some other things that you may not want to deal with. So you really need to look very closely at the design of the roof support structure so that you might be able to take advantage of the best possible connection detail that gives not only the homeowner the most energy efficient structure, but allows you to put the project up quicker and perhaps save a few dollars in terms of the engineered lumber components that you didn't have to buy because you didn't need them in those panels. Again, the design benefits and the features that we look at when we're working with SIPs is we've got the sloped cathedral ceilings, we've got nice big active dormers, and we're going to show you some doghouse dormers and how we can incorporate the SIPs into this doghouse dormer design. We have the conditioned and usable attic space, so that's one of the advantages of incorporating the SIPs into this roof scenario. If we talk about things like bonus rooms over garages and rooms that might typically be either so cold or so hot they're hardly usable, now we've got a nice comfortable space because we're enveloping the entire structure, walls and roof, into this SIP envelope, and we get the best of all worlds. In these photos you can see we've got the simple doghouse dormer, which is a common element on so many residential structures, and here we now have an element that was designed in CAD, was cut in a CNC equipment perhaps, fits together very tight, nicely and neatly, and it's not filled with gobs of lumber that took a carpenter a half a day to figure out how to frame and put up, and by the time he's done, you've got so much lumber in it, you have no place to put insulation in it anyway. In this case, good design means that we've got a doghouse dormer that's usable, it's comfortable. You can actually walk out in that space and you're not enveloped with either too cold or too hot an environment. The roof support structure, what's holding our SIP panels up, is one of the most important things that you, the builder, or just as important, the designer, will look at. There's all kinds of different options that you can use to hold the roof panels up, and what you hold up puts point loads in different areas in the walls, gives you different dramatic effects from an aesthetic standpoint. You may want to see these large timber trusses that are beautiful to look at. You may not want to see anything up there, and you might want the nice clean lines that means you've got only a ridge beam and nothing more. You may want to deal with purlin beams or trusses. You've got all kinds of things to look at, and this shows a list of things that we can consider when holding up our roof panels or our entire roof system. If we're talking about ridge and purlin beams, the type of material, also you've got that option to look at. You may deal with LVLs, you may deal with a glue lam, it might be an exposed beam, and an architectural grade glue lam works wonderfully because it becomes now an architectural feature of the house. Not only is it an architectural feature, but it's also holding up your roof system. If the span gets so far, you may have to incorporate steel. It might be the most cost-effective way, or it might be, from an engineering standpoint, the only way that you can hold up a very, very large roof system. You may need to go to something like a PSL beam, or you may have to use or want to use timber because you're dealing with timber frame elements. And this is where you may incorporate a hybrid type system where a timber frame truss works very nicely in a dramatic great room area that holds your roof system up and also gives you that architectural feature that you like. When we start putting panels together, we look at things like the ridge, and the main ridge may incorporate, as you see on the left, a ridge beam, which is your structural component, and then the panels that come in on top of that and are attached to that ridge beam. You can see in this detail as we have a joint between the two panels, the left and the right panel, that are then sealed, and this is a critical area of sealing. So from an installation standpoint, this is one that we harp on quite frequently because this is where that warm, buoyant, moist air tends to congregate in our structure, and we want to make sure that it's properly sealed. So this kind of sealing methodology that you see on the left gives us the opportunity to go to a complete foam enveloped structure or a nice ridge beam or a ridge connection that is fully insulated and isn't going to let any air leak out. If we don't want to go with a single ridge beam, we actually have the option of getting rid of the ridge beam altogether and going with offset ridges or purlin beams. And now we've, in essence, shortened the span of that roof panel. We've put the panel into a multi-span condition, and we've allowed the end of the panel, which is the ridge, to be tied to the opposite plane or the opposite roof plane, and then incorporate some of the loading over into that. This offset ridge detail works very well in not only holding up a roof, but in some cases, once we frame that off, we have a perfect area to incorporate some of the HVAC systems or the electrical components into a conventionally framed false ceiling that works very well to satisfy some of your trade's concerns about working inside of a roof SIP. Now, the other roof details that you need to look at are valley beams or valley supports, as well as hip ridges and the support of a hip within a roof system. You can do it in a number of ways. The one on your left shows a hip ridge beam, which is supporting both roof planes that come together into this valley area. Again, it's very important to incorporate the ceiling that is going to be underneath that valley, just as if it was a hip. You also need to make sure that no air is going to be moving up through there. But from a design perspective, you're looking at how do we hold this thing up. The one on their left is using a simple support beam that's carrying that load, and the picture on the right is showing actually a truss. So this might be a ridge or a hip ridge where you're using a truss system to carry the support of those roof panels. Just another way to look at it. In some cases, we can incorporate the support of either a hip or a ridge with internal beams. So the beam, whether it be a valley or a hip, might incorporate the structural element inside the panel. This gives us a nice clean line without any of the interference of the support element exposed to the inside. As you look at the photo on the right, you can see this doghouse dormer, and you can see that that valley connection where the roof panel of the doghouse dormer ties into the main roof panel, and we don't have that support beam underneath it. It ties very nicely together with the skin to the skin of those two panel planes, and it cleans up very nicely. There's a limitation as to how far we can do this because of the loading applied to the panel. Can't necessarily go great distances. You're much better to support in long distances with that beam underneath. Now, one of the things that people will sometimes look at when they're dealing with SIPs from an architectural perspective is the aesthetic view or the look of the overhang. They look at big, thick SIPs and they think, oh, I'm going to get a big, thick, chunky, fat overhang that I have to deal with. And this detail that you see here is one that incorporates the same thickness panel, the same pitched roof, but two very different ways to handle the details. We throw this out here just to show you that good design and good thinking about how you incorporate that design gives you the aesthetic look that the architect might be going for or the homeowner might be going for. The one on the left shows a plumb cut roof panel, and when we plumb cut that roof panel, we're left with a fascia height that's greater than 12 inches. It doesn't necessarily look that attractive on most residential houses, whereas the one on the right shows that the panel was left square cut, which actually makes it easier for you, the builder, to deal with, and then you're using a combination of blocking and conventionally framed fascia and soffit details that give you now a fascia height of something well under 12 inches and much more agreeable from the design perspective when using thick panels on a pitched roof. As we wrap up, I want to talk about roof penetrations. In the best of all worlds, with a SIP envelope that's energy efficient and designed to be durable, and we're worried about things like moisture and heat, in the best of all worlds, we would never have any penetrations through our roof. The reality is we can't usually do that. But where we do have penetrations, I'd like you as the builder to think about, one, where those penetrations occur, and more importantly, how you're going to seal up those penetrations. From a design perspective, you need to control where these penetrations happen. If you're dealing with things like plumbers who want to put vents through the roof, let's think about how we can combine them to have the fewest possible, and where are we going to put them through the roof. One of the tidbits that I like to point out to builders is wherever you're going to have penetrations through your roof, just because in the future you may opt to add some type of a solar system on a panel, it makes good sense to make your penetrations through your roof always on the north side of your structure. Leave that south side open. It makes future changes to the house and the acceptance of an add-on solar system so much easier when you're not having to go in and start moving things like plumbing vent stacks. If you're dealing with a skylight through a roof panel, make sure that we know what size skylight and where that skylight is going to be before we start designing the building. That skylight opening, and depending upon the size of it, may change the engineering capacity of that panel in a big, big way. And we don't want to put up a engineered system without any openings allowed for the design, and then after the fact have a homeowner decide that they want to put a huge skylight right in the middle of their room, and we've got an engineering issue to deal with. These are things that need to be determined before we start dealing with it. And ultimately, from a design perspective and a design and engineering perspective, we have what might be referred to as extreme engineering. We're not going to talk about extreme engineering other than to describe things that might come up when we start talking about extreme engineering, and those are high wind zones, places where we have massive snow loads, and we're starting dealing about snow loads where the ground snow load might be in excess of 60, 70, or 80 pounds. You've got massive loads, and engineering is absolutely required. I'm not saying the panels can't do it, but the engineering has to go into determine what thickness panel, how far the panel spans, what holds that panel up so that it's going to work to carry those loads. In addition, if you get really high tall walls or you get massive overhangs, you have to start dealing with things like wind uplift. And it's this wind uplift that the designer needs to take into consideration to determine whether or not they have the proper fastening schedule, because if you don't have enough screws in your roof panels to overcome the wind that hits that building and then tries to rip the roof panel off, you're going to have a problem. It's these types of things that you need to be paying particular attention to. And every state has different issues that you need to deal with. So the builder that I might be talking to in the Southwest deals with far different issues than the one up in the Rocky Mountains or the one down in the Southeast. And ultimately, you've got seismic issues. Seismic issues are predominantly dealt with on the West Coast. There's a few areas on the East Coast that we have to deal with them, and these issues are far beyond the scope of this presentation. But albeit to say that the testing is being done that shows that panels certainly can handle the loads that are applied in seismic issues, and they can be designed into that panel package. What should be considered in all cases is what are the environmental influences on a panel package such that that designer and the engineering that goes into that design is all considered so that you, the builder, know that the package that you're putting up has got the right design with the budget constraints dealt with to satisfy the engineer and allow you to put up the system that's going to be the best possible one for you. That's going to finish this module up for today, and we're going to step up to the next module, number 3, for the BEST program. We'll see you soon.